There are lots of interesting relationships between these trigonometric functions. We call those identities. Just to sort of illustrate one, if we graph sine squared of x, and by the way, this is a notation that we encounter. Notice that the exponent is on the name of the function. What it means is to take sine x and multiply it by itself, so sine x squared, which would be sine x times sine x. But that's such a common function that we actually just name it sine squared of x. So if you see a 2 or an exponent here on the sine, usually that just means to take sine times itself that many times. If it's a negative exponent, particularly if it's a negative 1, be careful though, that usually indicates the inverse function when it's on the name of a function. Okay, so if we graph sine squared here, I've got a graphing utility here and I've put it in there. If you look at it, this looks a lot like either a sine or a cosine function. The only difference is it looks like the period is shorter. Normally it takes sine and cosine 2 pi to go through a complete cycle, but this is going through the cycle in a total time of pi. It just looks like a sine or a cosine that's maybe been flipped and shifted and smashed a little bit. And in fact, if you graph this function, which is the cosine, which has been speeded up so it's moving twice as fast, so its period would only be half as long, with a flip here and a little smashing because we're dividing the outside by 2 and then we're shifting it up by 1/2. If you draw that graph, you actually see the same thing, so that it just lined up right over the top. This is an example of an identity. It's something, it turns out this is always true no matter what the angle is. The sine squared of x is equal to 1/2 minus 1/2 the cosine of 2x. Sometimes we combine that into a single fraction. Since we have this denominator of 2, just take 1 minus the cosine of 2x and divide that whole thing by 2. That would be the same. So that can be kind of handy if you think about sine x. That's kind of complicated as a function. Sine squared is kind of complicated, but you can relate it back to just some simple transformation of your basic cosine. That's kind of handy. It can simplify problems sometimes. So these identities actually can be very helpful, and there are several identities that you need to know in order to be successful in calculus. So the first identities are the Pythagorean identities. Remember, for a particular angle, so here's some arc length along there, right? That's some angle alpha. And if we're on the unit circle, so that the radius of the circle is 1, then in that special case, this horizontal component is the cosine of alpha, and the vertical component is the sine of alpha. If you look at this, this is a right triangle, right? So if you take the sum of the squares of the two shorter sides, you should get the square of the hypotenuse. This is one of the Pythagorean identities, the most important one. So that cosine squared plus sine squared, as long as you're taking the cosine and the sine of the same angle, then you're going to get 1. Of course, we also have a similar identity. Remember when we defined the tangent, we drew this vertical tangent, and then this whole distance was the secant of alpha. This is on the line that cuts through or intersects the circle, so it's the secant, and this is the tangent line. So this component here was the tangent of alpha, and you can see they make a right triangle as well. This length, since the radius of the circle is 1, this whole length here is 1, and the cosine is just that short bit of it. So this whole length is 1, so the sum of the squares of the two short sides would be 1 plus the tangent squared of alpha equals the secant squared of alpha. We get a similar deal if we look at the cotangent and these two legs and the cosecant, which would be this distance in this case. So, alright, you can see this is also a right triangle here, so you get cotangent squared alpha plus this distance is 1, so plus 1 is equal to the square of this distance, which is the cosecant squared. So those are our three Pythagorean identities. Now, you don't actually have to remember all three, because notice if you just have this one down, which is pretty obvious from the pictures that we have for cosine and sine, right, for the way they're defined on the unit circle. If you just have this down, then if I divide both sides of this equation by cosine squared divided by cosine squared would be 1, sine squared divided by cosine squared would be sine over cosine times sine over cosine, so that's tangent squared, and 1 over cosine squared would be the secant squared. Or, if I divide both sides by sine squared, cosine squared divided by sine squared is cotangent squared, sine squared divided by itself is 1, and 1 over sine squared is cosecant squared. So if you get this one, it's pretty easy to get the other two. Or you could just remember the pictures that define all six. Whatever works. Okay, so those are pretty key. Those are probably the most important identities that we have for trig. So the Pythagorean identities were kind of geometrically obvious. Another set of identities that are kind of obvious are the cofactor identities. Remember, when we think about sine, we started here. The sine here is 0, and then the sine of pi 6 is 1/2, and they go up from there. With the cosine, though, since it's the horizontal component, you start here and start counting that way. So notice that the cosine of this angle is also 1/2. So there's a relationship here between sine and cosine. So if this is your angle, whatever it might be, say alpha, then to come backwards here would be to turn a whole pi halves and then remove alpha. So you would, if you turned pi halves and then removed alpha, you'd be in sort of a symmetric position. The sine at this angle would be the vertical component, and the cosine at this angle would be the horizontal component, and you can see that those two numbers are going to be the same. So we could say that in symbols, that the sine of some angle alpha is the cosine of pi halves minus alpha. That's the first cofactor identity. It also works for cosine, right? Whereas the cosine, if our angle had been alpha, was like this angle here, if that was alpha, then the cosine at that value, the horizontal component at that value, would be the same as the vertical component if you turned a whole pi halves and then came back that corresponding amount alpha. So you get the same, the cosine of alpha is the sine of pi halves minus alpha. So those are just a couple of identities that are pretty geometrically clear. We could do something similar for the others, but we can just rely on their definitions. The tangent of alpha would be the sine of alpha over the cosine of alpha. But then from these other two identities, the sine of alpha is the cosine of pi halves minus alpha, and the cosine of alpha is the sine of pi halves minus alpha. And cosine over sine is cotangent. So this is the cotangent of pi halves minus alpha. Okay, so you can do a similar thing with cotangent. You'll see that the cotangent of alpha is the tangent of pi halves minus alpha. We could also do that with, say, secant or cosecant, because the secant of alpha is 1 over the cosine of alpha, and the cosine of alpha is the sine of pi halves minus alpha, and 1 over the sine is the cosecant. So you get the cosecant of pi halves minus alpha. So there's a relationship between secant and cosecant. We've noticed before that it looked like secant and cosecant were just shifted versions, and this is one way of seeing that in symbols. Also, pretty clear the cosecant of alpha is going to be the secant of pi halves minus alpha. Okay, these are sort of handy. In particular, you can see that every sine is related to a cosine, right? Every tangent is related to a cotangent, and so on.